Hi guys, welcome back to functional analysis. We've just proven the Fredholm alternative, so the statement about if you have a compact operator on a Banach space and you look at identity minus that guy, then the resulting operator is going to be injective precisely when it is surjective. So that's a remarkable result, which further emphasizes the importance of compact operators on Banach spaces. Now, we have already seen early on when we were discussing the spectrum that, of course, in infinite dimensions, if you look at operators on infinite dimensional spaces, that injectivity and surjectivity no longer go hand in hand. For instance, there was the example about the right shift, say on small L2, that guy had no eigenvalues, so lambda I minus the right shift is always going to be injective, but there were plenty of elements in the continuous and the residual spectrum, so surjectivity nevertheless is violated, although injectivity of lambda minus the right shift is always given. Now, back then we didn't know what compact operators or compact linear transformations were, so now for that reason I want to do another example that will clearly display that really in the Fredholm alternative you need the assumption that you're dealing with compact operators. All right, so the example is displayed here. It has to do with continuous functions on the unit interval 0, 1, supremum's norm. That guy is a Banach space that we discussed very early on in the module. The underlying scalar field here I take for now the complex number field, and our operator will be, well, this guy here. So this is multiplication by the independent variable from the left, right? So t just sends your function to itself but multiplies the guy with x from the left. Now I claim, first off, that this guy is not a compact operator on the underlying Banach space X. And why is this? Well, compactness means it maps bounded sets into sequentially compact ones. So what I'm going to do now is I'm going to construct a bounded sequence and show that the image sequence under the map T does not have any convergent subsequence. And then we will know it's not compact. So here's the guy, fn of x. So that's a sequence of functions, going to be oscillatory, sine to the 2n pi 2x minus 1. That's obviously a continuous function. So the sequence formed out of all the fn's is going to be a sequence in my space. C0 is a bounded sequence because the trigonometric functions, their complex modulus, or here it's the absolute value, is bounded by 1 above. It's a bounded sequence, and however the image sequence, that is to say t sub xn, has no convergent subsequence. Okay, and how to see this? Well, actually it turns out this is a calculus optimization problem. So if you look at, say, well, if n is above m, you can do it the other way around as well, tfn minus tfm, so you have to estimate the infinity norm. Okay, this is here since we're dealing with continuous things. Now I'll write the maximum instead of my usual convention of writing the supremum. So then you have just this. That's just the definition of the operator norm. But now calculus kicks in, because what you can do is, well, you can give this to a student in calculus, call this function gx, which depends on n and m, and ask them to find local extrema in this interval, right? And the extremum will exist because of Weierstrass theorem. You got continuous functions on a compact interval. And so if they do this, they will figure out the following thing. Well, I have to write it on the next page, and do check if this is all correct. So it turns out this guy is going to be at least 1 over 2, and then the maximum, and actually all the magic, the lower bound you will find from 0.5 to 1, not from 1, from 0 to 0.5. So then you will have this fn of x, fm of x, and that guy is always at least 1. So that whole thing is not gonna go below 1 over 2, right? So, but that means I can be a bit more precise, and actually the lower bound is achieved, and that's what you will find out if you do the calculus optimization. Let me move this. This is our upcoming topic further down here. The optimum or the minimum here is achieved at these points x sub m, which is 1/2 1 plus 2 to the minus m plus 1, which is a point in 1/2 1. It creeps up to 1/2 as m goes to infinity. Okay, so that shows in particular that that map is not compact, right? Because, well, if txn minus txm in the infinity norm is always bigger than 1/2, then no subsequence thereof will be convergent. Okay, good. Moreover, I claim the Fredholm alternative does not apply, but that's now not a surprise, right? Because apparently it's not compact. Moreover, the Fredholm alternative does not apply. Okay, so here's some knowledge. So first, I claim that the point spectrum of our operator is empty. And why is this? Okay, there will be some exercise about this, so where you have to rigorously prove this, but I will give the argument, at least for the eigenvalues, I will give it now. So if you're looking for the point spectrum, you have to set, well, you have to solve the eigenvalue equation, tf is equal to lambda f, for f non-zero in your space, right? That's what you're looking for. The zero, not the zero function. Yeah, okay, but this means then for all x in 0, 1, you must have that tf of x, now I evaluate it, is equal to this. Oh, one bracket too many. F of x, and by definition this is just x f of x, right? So, and then what you have here is x minus lambda f of x is equal to 0, and this must hold for all x in your interval from 0 to 1. Yeah, but how can this only happen? Notice this bracket here, it vanishes only at one point, namely x is equal to lambda. Yeah, but this whole identity has to hold for all points in 0, 1, so this can only happen, remember you're dealing here with continuous functions, if that function is identically 0, right? And that's why you don't have any eigenvalues, okay? That's the argument. I will erase it again. As I said, this will appear on the exercise sheet, but that's the argument for the point spectrum, right? So we have this. So in turn, you have that 1 minus t is injective, right? Because the guy doesn't have any eigenvalues, right? It's injective, while at the same time, and this I will leave to the exercises, while at the same time, well, the spectrum is not empty, right? Because we're working over a complex Banach space here. So where's the spectrum? Well, the spectrum is the interval from 0 to 1. It's real, it's not surprising because the guy is self-adjoint. R. So in turn, lambda I minus t is not invertible because not surjective for lambda in 0, 1. So in particular at lambda equals 1, that guy is not invertible. So although you have injectivity of identity minus t is not surjective. Right? So Fredholm alternative does not apply, but there's a good reason for this because the guy is not compact. Right? Good. Excellent. All right, so now, having this, now we move on to our next big theorem, which is the first building block for the spectral theorem, and it's called the Ries-Schauder theorem. So Schauder, that guy we already encountered once in Schauder's theorem, stating that if T is compact linear transformation, then that happens precisely if the dual transformation is compact, as long as you're working over Banach spaces. All right, so now here's the theorem, Ries-Schauder. If you have a compact operator, T, on a Banach space X, then the spectrum minus 0, remember we already know that 0 is in the spectrum of any compact operator. That's because the identity operator in infinite dimensional Banach spaces is not a compact operator, right? So 0 is certainly in the spectrum. But if we throw out 0, then the rest is a discrete subset of the underlying field, well, minus the 0, obviously. All right, what does this mean, discrete subset? Well, a set of points that you can enumerate, lambda sub n from 1 to capital N. Capital N could be infinity. Of points, but if it is infinity, then they can only accumulate at the origin. They can not accumulate anywhere else, right? Each lambda n, moreover, and that's now important, is an eigenvalue of finite geometric multiplicity. So the geometric multiplicity is defined here precisely as in linear algebra, the dimension of the, well, eigenspace, so of the kernel lambda ni minus t is finite for all n. Right? So that's a remarkable theorem. It completely classifies the spectrum of a compact operator on a Banach space, except for 0. So for 0 in general you can't say much. It is in the spectrum, but whether it is an eigenvalue, whether it is in the continuous or on the residual spectrum, that always depends on the given, t at hand. However, all the rest, if there are any, this theorem doesn't say that there are eigenvalues. It just says, well, suppose there are some. No, it doesn't say that. So it doesn't guarantee existence of eigenvalue. It just says if the spectrum, sigma t, if you throw out 0, then whatever is in there might be nothing in there, it is going to be an eigenvalue of finite multiplicity. That's what it's going to say. Okay. And the next theorem, the Hilbert-Schmidt theorem, will assert that the spectrum is not empty, at least if you are over Hilbert spaces. Okay, but right now we don't know this. Okay, nevertheless, this is a very nice theorem, and it is a consequence of the Fredholm alternative. All right, so the proof, it won't take too long. Let's get started. So if lambda different from 0 is not an eigenvalue, we will have to spend most of the time here proving the discreteness. The other parts are easy consequences of the Fredholm alternative. So if lambda different from 0 is not an eigenvalue of t, then identity minus, okay, lambda is different from 0, so I can divide by it. And this guy here is lambda minus 1, lambda I minus t. Okay, so what do I know now? Well, if lambda is not an eigenvalue, this means this fella here is injective, the yellow underlined one. And that factor out front here doesn't change that fact, it's just a scalar, right? So that right-hand side is injective. Yeah, but that means the left-hand side is injective, and, oh, here's a typo, it's not the identity, it is t. So what is the left-hand side? Well, it is identity minus something compact. Right? Because t is compact and you can multiply anything compact with a scalar. Remember, they are norm-closed subspaces, the compact operators. So this guy will be compact. So what you learn from this equation, assuming that lambda is not an eigenvalue, you learn that the left-hand side is injective. But the left-hand side is identity minus compact, so the Fredholm alternative says then the left-hand side has to be surjective. Hence, the right-hand side has to be surjective, so it is now both injective and surjective, so bijective. And since you're dealing here with operators over Banach spaces, the inverse mapping theorem guarantees existence of a bounded inverse. All right, so that means in turn, by the Fredholm alternative, that then this lambda is not going to be in the spectrum. All right, so and that's it. That already tells you that all the elements sigma t without the 0 are going to be eigenvalues. That's that one line, which is a consequence of the Fredholm alternative. All right, now we have to do the finite geometric multiplicity and the discreteness. Okay, if on the other hand lambda different from 0 is an eigenvalue of t, then, that's also easy, because we had this little proposition that led to the Fredholm alternative. So if you have this kernel, then you can factor out again that lambda, get it like this, the kernels don't change. But the kernel of identity minus compact, which again you are facing here, is always finite dimensional, right? That we already know, right? And so by a previous result, that's the proposition right before the Fredholm alternative, the dimension of kernel lambda I minus t is finite. Okay, excellent. So it now remains to prove the discreteness. To prove the discreteness of sigma t without 0. Okay, and thus, what does this mean? Thus, to show that for any epsilon positive, there are at most finitely many eigenvalues lambda of t with lambda outside the disk of radius epsilon. Okay? Assuming the contrary, notice here we are assuming that eigenvalues exist. We are not proving that they exist. That will be achieved by the next theorem. Okay? Assuming the contrary, there exists an infinite sequence, say lambda n, of eigenvalues with lambda n, all in modulus absolute value above epsilon, and we may assume that all the terms of this sequence are distinct from one another. If there are some that are equal to each other, just throw them out. Okay, for I different from j. All right, but what do we know about the spectrum? The spectrum is compact. Okay, so that means that sequence has to be a bounded sequence, right? Yeah, that's true, but actually that's not what I'm going to use. So since the spectrum is compact, there must exist now a convergent subsequence, right? Because compactness implies sequential compactness. Okay. Right. I mean, the sequence, my argument. Okay, I can argue with the compactness, or I can just, yeah, the compactness is the good one. Yeah. Bolzano-Weierstrass, that's more precisely, right? You have a bounded sequence. Our scalar field is either the real number field or the complex number field. You got a bounded sequence in there, so that has at least one convergent subsequence. Yeah, that's Bolzano-Weierstrass. Okay, it's compact. There exists a convergent subsequence lambda nk, subsequence of the lambda n's, say lambda nk goes to lambda as k tends to infinity, with, since all those terms are outside the disk of radius epsilon, so will be the limit. But for each, now let's abbreviate the notations here a little bit. So mu k is lambda nk, so that I don't have to run around with these two indices all the time. There, because these are eigenvalues, there exists an eigenvector xk, non-zero by definition, of unit length. This I can achieve without loss of generality. These eigenvectors are always non-zero, so you can divide out their norm and you're good. Of unit length and eigenvectors. Remember, I assume that the sequence up there, all the terms are distinct from one another, and now that means in particular that the eigenvectors corresponding to distinct eigenvalues are linearly independent. This is a fact from linear algebra that carries over without any modifications to this context. Are linearly independent. Consequently, and now we're going to use Ries's lemma again. if you define x sub k minus 1 as the span of those guys, so those eigenvectors, they're linearly independent, so that's going to be a k minus 1 dimensional space. It is a closed, since finite dimensional, and it is a proper subspace of, well, the next bigger one, x sub k. Right? That's clear. Hence, by Rees lemma, we can select something in the complement, say xk prime. Well, okay, it doesn't matter that it's in the complement, it's in the bigger one. It has unit length, but it stays distance 1 minus epsilon away from the capital X sub k minus 1 of unit length, so that distance xk prime to xk minus 1, well, again, let's do epsilon over 2, 1 over 2, so a half. All right. However, using that xk prime, well, it's of course a linear combination of the, because it's in the span, right? So it's a linear combination of those first x sub k guys, the first k of those x sub I guys, with alpha I in f. We derive yk. That's just an abbreviation for mu ki minus t xk prime. So what do I have? So xk prime is an eigenvalue of t, so I can use the eigenvector-eigenvalue equation for the second part, and I can use the expansion, which is up here, for both, right? So then you will have that this is equal to I1 to k. Then I have mu k. Minus eigenvalue eigenvector equation acting on the xi spits out a mu I, and then you have alpha I xi, right? That's correct. Yeah, but now you see when I is equal to k, then you have a zero term there. So actually that sum, it truncates at k minus 1. Right? So this is mu k minus mu I alpha I xi, and that's of course an element in capital X sub k minus 1. Consequently, for any k above m bigger than 2, we have mu k minus 1 txk prime minus mu m minus 1 txm prime. Okay, of course I'm heading for a contradiction with the compactness of t. At the moment that we want to prove the discreteness there, we haven't used the compactness of t yet, right? So, but now it will come. So now first, what do I have? Well, I can use the equation that I had earlier. So remember y of k, it's on the previous slide, but I don't want to switch back and forth all the time, so I'll write it here. So we had this guy here. So this will give me mu k minus 1 yk. So what I'm doing is I'm replacing this guy here with the corresponding piece from up there, and then I will have a yk there, and then the ym, I switch around the signs, but that's okay because here inside a norm is this here, okay? But now we just figured out that it's still written up there, that yk, this was here, let's write it here, that the line started on the previous slide, that yk is in xk minus 1. So this here is in xk minus 1. Yeah, but if they are, remember they are nested upwards, those x sub k's, then this here is at least in, well, it is in xm, which is in xk minus 1, because m is strictly less than k, right? So these two guys, they're up front, they are in x sub k minus 1, which is the subspace. So that here is at least as big as the distance of xk prime to xk minus 1, which is bounded by 1 over 2 by Rees geometric lemma. Good. In summary, what does this tell us? In summary, this sequence, mu k minus 1 txk prime, has no convergent subsequence. Has no convergent subsequence, and since well, mu k, this was lambda sub n sub k, as k goes to infinity, it goes to lambda. Well, the same is true. The same is true, and remember those lambdas, they are different from 0. They're outside the disk of radius epsilon. The same is true for the sequence where the mu sub k minus 1 are erased. Okay, so what I'm trying to argue here is the same is true when I erase this little piece here out front. Okay, and that works. Okay, so but that's a contradiction but to the compactness of T. But this contradicts the compactness of T, given that the sequence of the xk primes, they are normalized to 1, is a bounded sequence. Okay? Since xk prime is bounded. Okay? So our assumption was false, and hence sigma point spectrum without 0 must be discrete. And that's the end of the proof of the Riesz-Schauder theorem. Okay, excellent. So it used several steps up front. The Fredholm alternative to deduce that, well, injectivity gives you surjectivity for free, and then in turn, if lambda different from 0 is not an eigenvalue, it's going to be in the resolvent, right? So that is to say, all the points in the spectrum, except for 0, if there are any, assuming there are any, are going to be eigenvalues. Then we prove that they have finite geometric multiplicity. This comes from this proposition before the proof of the Fredholm alternative, and then we had to work harder to establish that the spectrum is discrete. It used Riesz geometric lemma again, and then derived a contradiction to the compactness of T. All right? Very nice. So now that we have Riesz-Schauder, now the next theorem, and that was going to be the longest ever here in this module, is the Hilbert-Schmidt theorem. We will actually show that there are, well, eigenvalues as long as you're working over certain Hilbert spaces. Okay, but this is going to be a very long proof, and we will need some time for that. Okay, I'll see you in the next video.